All right. Well, welcome everybody to our quarterly Sense Network meeting. So glad that all of you are here joining us today, and we have a nice turnout. I know many of you, but certainly not all of you. My name is Josh Ehrlich. I'm faculty here at University of Michigan and one of the PIs of the Sense Network, along with Jennifer Deal, who apologizes that she was unable to be here today due to some family commitments. But we're delighted to welcome you today, and I think we have a really interesting and engaging meeting ahead. Um, and since we have quite a bit we want to pack in, we'll go ahead and get started with some announcements, and then we'll move into a lightning talk, which Toria Liu will be giving, and then we'll hear our keynote presentation by Dr. Jenny Campos, which will succeed the lightning talk. So without further ado, we can get into announcements. Suze, if you don't mind sharing slides. So the first thing I wanted to announce to the group is that we've put together as part of the Sense Network a course that's been developed for researchers, clinicians, trainees, public health professionals, and really any other learners who are interested in receiving an introductory approach and understanding to sensory health and aging. We've titled this, as it says on the slide, Public Health Approach to Sensory Health and Aging. The course is completely free. It's comprised of lectures delivered by Sense Network members and principal investigators and co-Is, and a series of podcasts. It's hosted on this platform called Johns Hopkins Course Plus, but anybody can register. It's open for anyone. It's free. You don't need a Hopkins affiliation. You can just follow the QR code. It's also linked from our website, and I believe there's a link in the chat as well. Lectures really are rather broad. They cover biology, epidemiology, measurement, across vision, hearing, and olfaction. And then the podcast discuss applications of public health perspectives to sensory interventions, policy, and future directions in the field. So we hope that some of you will take an interest and take the course, either all of it or parts of it, and please provide feedback so that we can iteratively improve the course over time and expand the course to meet the needs of an expanded group of learners. Next slide. For those of you who are not who are on social media but not engaged with the Sense Network on social media, we have QR codes here for the Sense Network's LinkedIn and Instagram accounts. Please, if you're on those platforms, and also in the chat, if you're on those platforms, please engage with us. We'd love to hear from you. We'd love to also help to promote the great work that all of you are doing to our network. And so with that concludes our announcements. You can switch slides here. I'm really pleased to introduce our lightning talk speaker today, Toria Liu. Toria will be talking to us about hearing and Alzheimer's disease related plasma biomarkers. Toria is a recent Master of Science in Epidemiology graduate from Johns Hopkins University. During her master's, she's been a trainee in the Cochlear Center. And today she's going to talk to us, as I said, about hearing and Alzheimer's and disease-related plasma biomarkers, and tell us just a little bit about herself and her interests and how she came to this field. So we're delighted to have you today, Toria. And with that, you can take it away.
Thank you so much for your kind introduction, Dr. Ehrlich. And thank you so much for having me. My name is Toria Liu. I'm just graduated from epidemiology in Johns Hopkins, and right now I'm a research assistant here. So previously I got an MPH degree at socio-medical science at Columbia University. My research interest is sensory health among older adults and implementation science. So today I'm going to talk about a topic that I was presented at in last year GSA, but very, very excited that it's going to be submitted for a journal. It's going through all the co-authors is right now is going through the co-authors, and it's about the audiometric hearing and plasma biomarkers of Alzheimer's disease pathology, and also dementia-related neurodegeneration and neuroinflammation using the ARIC study. And the pathway between the hearing and plasma biomarkers is still unknown. Um, so we're going to study hearing with this association between the Alzheimer's disease pathology, especially A beta 42/40 ratio, and also p-tau 181. And those two are Alzheimer's disease specific pathology. And neurodegeneration and neuroinflammation plasma biomarkers is NFL and GFAP in our study. And these were taken as Alzheimer's disease non-specific plasma biomarkers. So as we all know that hearing is associated with cognitive decline in many studies. So we use global cognition as a positive control in our study. And we use ARIC NCS. We conduct a cross-sectional analysis using this population-based cohort in 4 US communities. And we have 1,120 community dwelling older adults aged 71 to 93 years old in after the exclusion process. And our exposure is continuous better year peer-to-peer average hearing, which was collected at with the six. Our outcome is plasma biomarkers because at visit 6 plasma biomarkers were only 123 people, so we also include plasma biomarkers at visit 5 and visit 7. So because of that, we adjusted for here time between measures of plasma and hearing. And we use weighted multivariable linear regression models. So the results, after all the adjustments, each 10 decibels worse hearing was statistically significant associated with higher plasma NFL and lower global cognition. But we didn't find a statistically significant association with amyloid beta 42/40 ratio, GFAP, or p-tau 181. And we can acknowledge that there were limitations in this study because plasma biomarkers were collected at different studies, different visit, so there was a mismatch. But we can make conclusions in right now our study is that worse peripheral hearing was associated with higher plasma NFL, and NFL reflect broader neurobiological process that are not specific to AD pathology. And we also call for longitudinal studies with repeated measures. And we also acknowledge that this is a really emerging field. So we saw a study saying that hearing is associated with GFAP, but we didn't find the association between GFAP and audiometric hearing right now in our study. So we're just looking for the result from other studies. Yeah, this is basically the talk and a bit about myself. So I want to share a journey to Xinjiang Uyghur Autonomous Region, and the view was just stunning. And our family got to a camping area, and there was a herbs, and we saw goats, and they wanted to escape from the sunlight, like it's very strong sunlight, so they hide it between the shades between the cars. So that was very interesting. And we saw random kittens showing up at the margin of the wheat field. And I took selfies with beautiful horses. So right now I'm a research assistant here for 1 year, but I always save my energy and looking for the next journey. Yeah. Thank you for listening.
That's great, Toria, and really, really love those pictures at the end too. Thanks for sharing that. It looks like a beautiful, beautiful part of the world. Um, I wanted to just open it up for any questions, any thoughts that people might have, or questions or ideas for further research for Toria and her team.
I have a couple of questions. This is Moises Klo from Hopkins. Very nice summary. I think it's great to hear something so well done and concise. So I have a couple of things. One is that using one analytical unit, 10 decimals, assumes that the relationship is linear, right? So have you checked linearity?
Yes, thank you so much for that. This is a really good point. So we have exploratory data analysis, and we specifically search the association between continuous hearing and also their association with plasma biomarkers and their association with EGFR and also BMI because those are very strongly associated with plasma biomarkers. So we also look into that. And we actually include the spline terms of BMI and EGFR. And it is also correspond to other previous studies that there was a nonlinear association about that. But and for the plasma biomarkers and hearing association, the association looks linear. So yeah, thank you so much for your point.
So one quick question.
Mhm.
Are you concerned about the informative sensory? I mean,
The
selection bias, I mean.
selection bias. Yeah,
You,
we. Mhm.
go ahead, please.
Um, for the selection bias, so we use the weighted model. So the weighted model was based from the weights at visit five, and the visit five, the selection is like select people with the MRI study and people without the MRI study. So I think we use the weights there, so like it accounts for some of the selection bias. But I don't think like I can totally like state that there was not no selection bias or any other bias here.
One final question.
Mhm.
I suggest that you look at effect modification by age. You do have a very broad age group. So
Mhm.
certainly people who are 90 are quite different from people who are 74 or something like that.
I see. Yeah, yeah. Thank you so much. That's also a great point. We'll look into that.
Thank you.
Thank you.
Great, great questions and great, very illuminating answers. Thank you all. Um, well, thank you, Toria. I think we'll move on now to our keynote speaker. We're going to hear from Dr. Jennifer Campos. Jenny is a Canada Research Chair in Multisensory Integration and Aging. She's Associate Director and Senior Scientist at the Kite Toronto Rehabilitation Institute, which is part of the University Health Network at University of Toronto. She's also the Chief Scientist of Kite's Challenging Environment Assessment Laboratory, which is a high fidelity virtual reality and simulation lab, and is a full professor of psychology and rehabilitation sciences at University of Toronto. Her research focuses on understanding how the brain integrates across multiple sensory systems, how these processes change with older age, how age-related changes to sensory abilities like vision and hearing affect functional behaviors such as safe mobility, which relates to falls prevention and driving safety, and how sensory health supports brain health overall. So it's really a delight to have Jenny here today, who's been a wonderful contributor to the Sense Network and a great colleague and friend. And so welcome, Jenny, and very, very excited to hear what you'll present today.
Great. Thank you so much, Josh. And you can see my screen, I assume, and can hear me okay. Great. So first of all, thank you so much, Josh, and thank you so much, Jennifer, for inviting me. These are really wonderful meetings and such an important contribution to this community and to this network. So thank you so much for that. Also, hello to a lot of familiar faces in the audience. Thanks so much for joining today, including some really valued collaborators. On this first slide, I have a picture actually of my mom, Marg, and her friend Barb, who are participants in many of our studies. And I like to start my presentations with this image because I think it's always important to have a guiding compass for a lot of the work that we do, and a lot of the work that we do at Kite and my own research is focused on aging well. And so she and many of her friends are inspirations for that. Okay, so to get started, I thought I would provide a little bit of context about where I'm coming from. So right now I'm just outside of Toronto, but I'm based out of the Kite Research Institute, which is in the that is the research arm of the Toronto Rehabilitation Hospital. So Kite and Toronto Rehab, a teaching and research hospital, fully affiliated with the University of Toronto. It's highly interdisciplinary. So we have computer scientists and biomedical engineers working alongside psychologists and physiotherapists, occupational therapists, nurses, and others. A lot of what we do there is focused on translational research goals. So the three pillars of our research foci are prevention, so preventing illness or injury from happening in the first place, functional restoration if someone has experienced an illness or injury, and then aging well. So how can we, encourage a long health span alongside a long lifespan? So as Josh mentioned in the introduction, we do have some infrastructure that we use at Kite that is unique. This collection of labs that I'm going to describe just briefly right now are called the Challenging Environment Assessment Labs. So these are high fidelity simulators that allow us to, for example, in Stair Lab, simulate different aspects of the built environment, like bathroom configurations and staircase geometry. Winter Lab, which in Canada is very important to understand safety and injury prevention in winter conditions. I won't talk too much about those today, but happy to answer questions after. What I will spend a bit more time talking about today are our labs in Street Lab and Driver Lab. So Street Lab is a multi-sensory immersive virtual reality environment that allows us to simulate the sights and sounds of challenging everyday environments. And then we have Driver Lab, which is one of Canada's most advanced driving simulators. It's a full car. It's completely surrounded by 360-degree field of view projection system and allows us to simulate things like rain through real water droplets on the windshield and real glare through robotic LED-based simulations. And so the reason that we have these labs is because is multifold. Really, we're interested in doing some fundamental and indeed reductionistic research. So as you'll hear about in a minute, a lot of my research looks at multisensory integration. So if you want to really strategically control and systematically manipulate sensory experiences, then virtual reality is a good tool to enable you to do that. But a lot of what we do is try to introduce ecological validity into the questions that we're asking to be able to generalize the research from lab to life. And so what simulators allow us to do is to have introduce these realistic challenges, but in a very controlled and safe way compared to other traditional lab environments, which are very important in their own right. The one other feature I'll point out, as it will become relevant later, is that all of those labs I just showed you, those 4 labs, they're modular and they're portable. So we have a big motion platform that you can actually move each of those labs, place them on this motion platform, and it will allow you to move anything that's on top of it with 6 degrees of freedom. And so this becomes important, for example, I think most obviously maybe in driving. So if you want to have the real physical accelerations or very similar analogous physical accelerations that you would get during real driving, you can put Driver Lab on the motion platform. Sometimes we want to look at balance reactions. And sometimes we want to look at vestibular perception or how people perceive passive movements using their acceleration detectors in their inner ear. And so the motion platform allows us to do all of those things. So just very quickly, here's kind of an overview of my research program. So as I mentioned, I'm very interested in multiple sensory functions. I always like to say I'm a jack of all trades and a master of none when it comes to the sensory space. We look at hearing and vision, vestibular function, proprioception, and touch. And most importantly, we're interested in how the brain integrates across all of those different sensory signals and how, when they're competing with each other, how does the brain reconcile that? We look at sensory function and multisensory integration with respect to several different kind of functional outcomes. Mobility from standing balance, falls risk, gait, navigation, and driving. Understanding how sensory health influences brain health and the role of sensory function and multisensory integration in communication. In terms of the populations that we most frequently study, includes sort of healthy older adults and typical changes in sensory integration across kind of the typical aging trajectory. Individuals with cognitive decline, including subjective cognitive decline, MCI, and dementia, concussion, and hearing loss. And today, I'm really going to be focused on, and looking at these with sort of hopefully guiding, future interventions and applications. And so today I'm going to be focusing on hearing loss and healthy older adult populations, and with a focus on mobility. So looking primarily at standing balance, contributions to falls risk, and at the end, driving. Okay, so why are we interested in hearing? Why are we interested in the effects of the associations between hearing loss and mobility outcomes? It is no surprise to anybody in this audience, I believe, that hearing loss is very prevalent. It affects many, if not most, older adults over a certain age. I think it's most often associated with communication difficulties. But what is maybe less understood or less recognized is that hearing loss is also a risk factor for falls. So we know that hearing loss increases the risk of falls by about 3 times, even with mild hearing loss. And while there's some mixed evidence, there's also some indications that hearing loss is associated with greater risk of driving collisions. And I mention here also, that's very familiar to this group, is that as hearing loss is also a potentially modifiable risk factor for dementia, there's probably some overlapping mechanisms between what's happening in the cognitive space and what's happening with mobility-related outcomes. Okay, so we're going to focus on these 2 things today. Okay, so interestingly, several years ago now, but a report by Statistics Canada, surprisingly in my mind, indicated that for people with hearing loss who were surveyed, the most commonly reported limitations were actually to mobility and agility compared to communication, memory, or learning. We know through many studies now, actually accumulating evidence, that older adults with hearing loss are more likely to develop difficulties walking, walk slower, have poor physical functioning, and are increased risk of frailty. As I already mentioned, that there's an increased risk of falling, and there's also a dose effect. So the more severe your hearing loss, the even greater risk of falling. So there's lots of epidemiological evidence to suggest that this is the case, but I think the mechanisms or understanding why that is, there's so much to be understood within that space. And so there are several different, likely not exclusive, likely co-contributing hypotheses or factors that are contributing to this association between hearing loss and mobility problems and falls. So it could be the case that older adults or people with hearing loss have poor spatial hearing. If you have poor spatial hearing, then you may not be able to use these orientation cues, these sound cues in your environment, interoral time and level differences to be able to stabilize yourself and stay oriented within your space. And also the environmental awareness of what's happening around you. And, we sometimes forget that one of the primary purposes of hearing is to be able to detect quickly things that we can't see. And so if you have an inability to do that or a poor ability to do that, it may affect your ability to stay balanced and to navigate within your world safely. It's also possible that that individuals with hearing loss may also experience vestibular loss. So because the auditory system and the vestibular system work in functionally similar ways, there's shared nerve inputs to the brain, it's possible that, for example, with age-related hearing loss, you may experience age-related declines in your vestibular sensitivity. There could be indirect mechanisms too, so social isolation. If your hearing loss is causing you to, stay home more, not participate, not be social, it can lead to cognitive deconditioning and physical deconditioning, which could put you at risk. And then there's the cognitive load hypothesis. So when you have hearing loss, listening effort can become pretty significant. And the effort that it takes to listen requires a lot of cognitive resources that may then take important other cognitive resources, which are ultimately limited from supporting other activities that you would be doing at the same time as listening, of which mobility and balance is something that we are frequently required to do. So the first set of studies that I will present today are really trying to tackle this question of whether or not cognitive load could be contributing to balance problems. And so we did this study in Streetlab. And so we did this with collaborators, including Kathy, who is in the audience today, and Dr. Karen Lee. And so in this series of studies, we asked, first of all, do older adults who are experiencing sort of general declines to hearing, other sensory systems, cognition, etc. So do healthy older adults experience more difficulty than younger adults when managing the dual tasks of listening while balancing at the same time? So having these kind of competing demands on limited resources. We asked, does balance get worse when listening gets harder? Increased load. And then briefly, I'll touch on some of the directions that we're going now, which is, can we do something about it if there are costs to managing these demands? Can hearing interventions and or cognitive training interventions support balance or reduce these costs in older adults with hearing loss? So several years ago now, we did this study in Streetlab where we had younger adults, older adults with normal hearing based on sort of audiometric profiles, and older adults with hearing loss. And we looked at while they were aided and while they were unaided. We had them standing in Streetlab, and you can see this is an immersive virtual environment. It was basically simulating a street corner in downtown Toronto. You can see that they're standing on a force plate. So we're basically measuring center of pressure measurements that was giving us an indication of their balance under different conditions. And so in this study, sorry, I'm just going to move my little pictures of you guys there. So in this study, we had a couple of different tasks. So we had a listening task and a basic standing balance task. So for the listening task, we used a competing talker listening task, which was the dichotics digits task. And I'll just play a little sound file here, and hopefully this works. And so the task of participants was really just to listen for the digits that were being presented at the same time and repeat back those digits. So here is the low load condition where there's only 2 digits.
3, 4,
So hopefully people are hearing those.
1.
Okay, so you can get an appreciation of the difficulty of that task. And then in the high load condition, there were 4 digits. So I'll play that.
4,
6,
1.
They have to repeat back all 4.
5, 3.
Okay. And then in the standing balance task, we also manipulated kind of the load or the difficulty level. So easy was if they were standing on the firm force plate, and difficult was when they were standing on a compliant foam surface. And they also did this with their eyes open, which was easier, and their eyes closed, which was harder. So just to summarize those different conditions, we had standing balance only, so there was no listening task, listening only, whereby they were just sitting down, and then the dual task, which was listening while balancing. And the primary measures I'll present today are looking at the listening accuracy, so the percent correct in repeating back those digits, and then postural stability or center of pressure path length. But I'm going to be presenting to simplify it, the dual task costs, which is what we were really interested in. So what are the costs of having to do this, do these 2 things both at the same time? And we were interested both in the costs to listening. So if you were just sitting versus if you had to stand up, did that compromise your listening ability? And then we were also primarily interested in the dual task costs to balance or postural stability. So when you had to stand stably while alone versus when you had to do that while listening at the same time, was there a cost to your balance when you had to do this sort of effortful listening task? And so what you can see here are the dual task costs. So greater values means greater cost. Older adults on the left and younger adults on the right. And you can see that yellow is that low listening load condition where there was only 2 digits. And then in this kind of pink color, there's the high listening load. So you can see that for older adults, even in that low listening load, they are already starting to experience some dual task costs to balance, so they became a little bit less stable. But you can see that once that listening task became quite difficult, then the costs to balance were quite significant. For younger adults, the low listening load didn't do too much, but you can see that once the listening load became higher, then even younger adults started showing some dual task costs to balance. When we look at the dual task costs to listening, interestingly, for older adults, so in yellow, this is the firm surface. So this is the easier surface to stand on, the easier balance condition. And in the pink is the compliant surface. So that's the harder standing condition. And so you can see that for older adults, they actually, when the listening task, or sorry, the balance task was fairly easy standing on this firm surface, they actually had a little bit of a dual task benefit to their listening performance when they had to stand up. But you can see that when the task became harder, when they're standing on a compliant surface, then now you're starting to see a little bit of dual task costs to listening performance. And you saw something similar, but not quite as big in the younger adults. And so using this paradigm, we were interested to know, well, what if you could perhaps reduce listening load by using a hearing device like a hearing aid? Would that reduce dual task costs? Or if you try to target the mechanism a little bit more directly, if you were to give cognitive training, specifically executive functioning training, would that also be beneficial in reducing these dual task costs by increasing capacity? And so very quickly, here we're looking at the unaided versus aided condition and the dual task costs to balance. And to keep things really simple, we've got our different sort of listening load and postural load conditions, but essentially there was no difference between the aided and the unaided. So in this very simple standing balance task, and under these dual task conditions, there wasn't a benefit to aiding, but there's still a lot of work to be done here, especially when we can look at tasks that really capitalize on the benefits of hearing aids. And I don't have time to go into all of the details for the cognitive training study that we did, along with Dr. Karen Lee and Walter and Kathy and others on this call. But we were able to, through this multi-week at-home tablet-based cognitive training program, executive functioning training program, see evidence in increasing cognitive performance, but importantly, the benefits to cognitive performance that happened over the course of the training also translated into reduced dual task costs when we tested them in Streetlab using that same paradigm that I just described. The caveat here is that this was effective up to a point, to which, in terms of the severity of the hearing loss, that the hearing loss was not too severe. As soon as the hearing loss was too severe, then we failed to see this transfer of training of the cognitive training task into that Streetlab dual task cost reduction. So that sort of is fascinating and implies that early intervention could be very important. Okay, so to summarize that kind of series of studies, we saw that older adults experienced greater challenges to balance when they had to manage the competing task of listening at the same time. Listening was more difficult during more challenging balance-related tasks, and there's still a lot of really interesting directions that we can take with respect to interventions that could support these kind of multitasking scenarios, including optimization and evaluation of hearing aids and cognitive training. Okay, so moving on to some of these other hypotheses that we have also evaluated, we're going to look at the potential of co-decline in the vestibular system of older adults with hearing loss using our motion platform. And so again, this is work that was done by many collaborators. So many of you, I'm sure, are quite familiar with the vestibular system, our inner ear balance organs that are really important for a lot of functional kind of self-motion behaviors and perceptions, including gaze stabilization and gait stability and spatial orientation. In this task, we were interested in vestibular perception, so people's ability to interpret passive movements when they have no other sensory information to use. So in the dark, with no auditory cues, and as much as possible, limitations of body-based information from proprioception. And so the main objectives of this research were to test that hypothesis about vestibular code decline and to ask the question, first, is vestibular perception poor in older adults compared to younger adults? And specifically, is vestibular perception poor in older adults with hearing loss compared to older adults with normal hearing? And so we tested those three groups. And the task was really simple. It was an adaptive staircase procedure in which they were discriminating between two intervals of movement and determining which was the larger movement. And so they were presented with one motion, then which was basically a series of sinusoidal motions, and then a second interval of motion, and they simply had to respond which of the two did they move more. And so obviously the movements start off very different and very easily discriminable. And then they become, the differences between those two movement intervals get smaller and smaller and smaller until we find the threshold. So that point in which they can no longer discriminate those two movements. And so smaller thresholds means that their vestibular perception is more precise. And so as I mentioned, we tried to eliminate all other sensory information that we could to try to isolate it as much as possible to the vestibular system. We had two different types of movements that we presented on the motion platform. I'll show a video briefly in a second. One was heave, so this is just very simple linear up and down motions. And then there was pitch, so that was rotated around the head, around the ears, in the forward direction, rotation in pitch. So here's what the heave motion would have looked like from an exterior view on the motion platform. And so they would experience a series of sinusoids, and then the interval would stop. They would get an interval of similar duration with a magnitude that was either greater or smaller than the original one, and they had to make those discrimination judgments. Okay, and here are the results. So here I'm plotting threshold values. So higher values are worse and lower values are better. On the left is the heave discrimination task, and on the right is the pitch discrimination task. And then we have plotted the older adults with hearing loss on the left, older adults with normal hearing, and then younger adults. For the heave discrimination, even though there's a pattern there that looks like the older adults with hearing loss did have higher thresholds, it wasn't significant. It was as a function of age. In the pitch discrimination, however, older adults with hearing loss did have a significantly higher threshold or worse sensitivity than older adults with normal hearing or younger adults. There that is. Okay, so in terms of the vestibular code decline, as an exemplar kind of study, and we're doing a lot more work in this direction, we saw that older adults with hearing loss did have less sensitive vestibular percepts for some movements. In this case, it was most pronounced for pitch. And it would be interesting moving forward to see whether or not vestibular training might be helpful for older adults with hearing loss. Okay, and now for my last couple of minutes here, and to switch gears a little bit, pun intended, we're going to look at how we manage the demands of listening in another mobility task, and that is driving. And so we're going to look at this with in younger and older adults with and without hearing loss. And again, with our amazing collaborators, the work, PhD work of Catherine, and along with Frank and Kathy. Okay, so we could use a similar kind of conceptual framework for looking at how we can understand the management of these dual task demands and the consequences to a mobility-related outcome in the context of driving, very similarly to what we did for falls and mobility, sort of gait and mobility problems. And so in this case, really, the question of whether or not this higher cognitive load or this load, this effortful listening during driving has consequences to driving performance. And so this was a study that we did in our driver lab simulator. Okay, so the evidence in terms of like the more general epidemiological evidence with respect to hearing loss and crash risks and adverse driving events, there's some indication that hearing loss leads to adverse events greater than individuals with normal hearing. The evidence is a little bit mixed. But the question is that if this is true and that hearing loss is associated with less safe driving or poor driving outcomes, why might that be? And so we know that driving relevant auditory cues can be supportive, and we have published work in this area as well, specifically that acoustical signals that come from engine noise, from the tire road rumble, from wind turbulence, that gives you some good indications of relative changes in speed. Of course, detecting and responding to alerts, sirens, warning system indicators is really important. So if you don't have access to these auditory cues, you can imagine that this may be consequential to driving performance. It's also the case that driving relevant listening tasks can be supportive of driving. So following GPS instructions can reduce cognitive load for some elements or some factors, but it can increase cognitive load or listening load on the other hand. And then, of course, driving irrelevant listening tasks can just be distracting and detrimental. So talking to a passenger, listening to the radio or audiobook, or of course, being on your cell phone. And so we asked this question, how do the tasks of listening, and here we're talking about more distracting listening tasks, driving irrelevant, and driving compete for shared sensory and cognitive resources. We use a similar paradigm to what I described earlier, single tasks when they just listen only, driving only, and then listening while driving. And then we look at the behavioral dual task costs to both listening and driving. But in this case, we're also curious about what was happening in the brain. We can often see similar behavioral performances. So for example, older adults with and without hearing loss may actually not show many differences in terms of their dual task costs. But the question is it the case that, for example, older adults with hearing loss have to work a little bit harder in order to maintain that same behavioral performance? And might we see differences in brain activation? And so for this study, we also used functional near-infrared spectroscopy, which is compatible with the driving simulator. So in study 1, we asked the question, are there greater dual task costs to driving while listening in older adults than younger adults? And in study 2, we looked specifically at older adults with hearing loss to see if these costs are even greater. And for that study too, we looked at behavioral and neurophysiological outcomes. So very quickly, we had our 3 different groups. This was done in driver lab. We had FNIRS looking primarily at the left lateral prefrontal cortex. We had easier driving tasks, which was just in a rural environment, a harder driving task, which was in a city environment, which required a lot more sort of attention and maneuvering. Our primary outcome was standard deviation of lane position. And then we had the listening task. For that, we used the connected speech task. We wanted to make it kind of discourse-like, conversational-like. So there was a series of sentences on a theme, and the participants just had to listen to the sentences and repeat them back. That was done in an easier listening condition where there was less background noise, and a harder listening condition when there was more background noise. And so what we looked at there was word recognition accuracy, or percent correct. So the results of the younger versus older adults. Here we're looking at listening accuracy. So this is the word recognition accuracy. So higher is better. In this kind of mustard color was just the listening alone. And then in blue is this easier driving. So this is where the dual task comes in. And then in the gray, this is the dual task under that harder city condition. And there's the younger adults on the left and the older adults on the right with this both easier and more difficult listening conditions. So the pattern is actually pretty clear. Not surprisingly, as sanity check, there was better listening accuracy in the easier than the harder listening conditions, in that +4 versus 0 dB. We did see that there were dual task costs to listening in the older adults, but not the younger adults. So when they had to listen and drive at the same time, there was costs to their listening performance. We also saw that there was the poorest listening performance for older adults was in this hardest condition. So this is when they had to dual task, it was in the city, and the listening was hard. Now looking at driving performance, again, it was a pretty clear pattern. Here's driving only in mustard, and then the easier and harder listening conditions in the blue and the gray. And in the left, we see the rural, so the easier driving condition, and city, we have the harder. This is driving performance. It's standard deviation of lane position, which means higher values are worse. So they're more variable in their ability to keep in their lane. So we saw that, not surprisingly, there was poorer driving in the city than in the rural. There was poor driving overall. There's a mean effective age in older than younger adults. There was poor driving in the dual than in the single tasks, but only for the more difficult driving conditions in the city. And this was only for older adults. That effect was only for older adults under the most difficult listening conditions. So when you are driving in the city with the hardest listening task. And I won't have time to go through all of the results and show you them graphically in the older adults with and without hearing loss. But to summarize, and really just to make it easier, I'm going to put in green the effects that were the same in the older adults with and without hearing loss. And in red is where the hearing loss group really differed. So not surprisingly for listening performance, there was poor listening accuracy in the hearing loss group. And for both groups, there was greater dual task costs in the most difficult condition, which is what we saw before. That was true for both groups. Interestingly, for driving performance, there was a main effective group, so that showing that the hearing loss group overall, irrespective of condition, had poor lane keeping abilities than the older adults with normal hearing. But again, for driving performance, sort of replicating what we saw before, there was greater dual task costs in the most difficult conditions for both groups. Now, interestingly, we looked at our FNIRS data, and the hearing loss group actually had an overall greater change in oxygenation concentration from the driving only single task to when they now had to dual task and drive and listen at the same time. So that difference was greater in the hearing loss group, which is suggestive of greater activation, perhaps due to greater listening load. Okay, so to summarize, we saw that both balance and driving related outcomes could be compromised when having to listen at the same time, especially for older adults. In some cases, older adults with hearing loss even more so. There's some indication that there may be some vestibular co-decline that goes along with hearing loss. In terms of interventions, which is still very much an active area of interest of ours, we didn't see in those really basic tasks that hearing aids improved balance outcomes during those simple balance tasks, but we did see a benefit of cognitive training, particularly in those for whom they had mild to moderate hearing loss. So overall, I think our program of research is really sort of focused on understanding these more multisensory and cognitive interactions during these realistic and complex tasks, and hopefully they may provide some insights into strategies for application and mobility and accessibility, and generally support healthy aging. So thank you so much to my team, and thank you for your interest and attention.
Jenny, that was really phenomenal. Such interesting research and such such relevance to so many individuals throughout the world. Aside from the research, the laboratory is just mind-boggling. It's amazing to see what you're doing, and all the technology you have to facilitate this research. It's really quite impressive. Um, I wanted to go ahead. We have about 8 minutes, 7 minutes, so I wanted to open it to questions. I certainly have some, but wanted to see what others were interested in learning more about. So please feel free to unmute or raise your hand if you have any questions. So maybe I'll start with a question then. Um, so I know that you spoke at the beginning about doing a lot of multisensory integration, multiple sensory integration work, multisensory, and talked quite a bit about integrating in the sense of dual tasking, hearing, and cognitive demand. What about hearing and vision when it comes to driving and walking? What do we know about how some of this either varies or is accentuated?
Okay, so I think one of the important things to point out is that we look at multisensory integration from a couple different perspectives. So the first one is that we know, in mostly coming from like really fundamental work, that when you have information from across several of your different senses, like vision and hearing, or vision and vestibular or touch, when it's congruent and it's redundant, it's telling you the same information about the same event or the same object, then usually the benefits are actually super additive. So you have a situation whereby if you just were able to see something or just able to hear something, especially when they're kind of, not well super threshold, the benefits of combining information across your sensory systems is really significant. So we know that to be true. Now, on the other hand, when we look at some of these other paradigms, like the ones that I presented today, now we're looking at how the senses are competing with each other, which is also different, right? So if it is non-redundant and not congruent, it's not telling you the same information. And a good example would be in the driving study that we did. They're listening to a series of sentences, none of which are relevant to the driving task. Then, of course, they're going to now be competing for resources rather than being beneficial. And so there's a lot of work that we've done in both of those contexts to understand how the fundamentals of multisensory benefits can be exploited, how that changes with older age, and how that's different if you have sensory loss. And then we've also looked at this other question of, when you have these competing demands across your sensory systems, how do you manage those demands? So, and to your question about, how have we looked at this across other sensory systems? I would say that in the presentation that in most of the studies that we've done today, vision was a bit it's critical but secondary, because we didn't do a lot of manipulation of the visual inputs or the visual information. It was really just there to create this ecologically valid and realistic situation that you would typically be faced with when having to listen and balance or listen and drive. So obviously vision is a critical element of everything that most of us do. But we've also looked at, in other situations, about what happens if you manipulate vision and how does that affect your balance, for example. So right now we're doing a study in Streetlab where we have, so one of, if, for example, older adults with hearing loss have clearly poor hearing, but also perhaps compromised vestibular sensitivity. If their vision is normal, does that mean that they're actually visually dominant or using vision to compensate for declines in their other sensory systems? If that were true, if we manipulate visual cues to self-motion, so for example, optic flow or the dynamic visual flow of information, which is what we use to support our balance and guide our behaviors, if we manipulate that information in virtual reality, does that create greater disturbances or greater problems or greater postural responses in people with hearing loss compared to people with normal hearing? So we do a little bit. I know it's kind of maybe skirting around your question, Josh, but so I guess the answer is that we've looked at all of those different sensory systems, both from a supportive multisensory super additive effect and also how they compete. Yeah.
Fascinating, fascinating. I think we have time for one more question. Yingxi, I think you you had your hand up first, so if you want to unmute, ask your question, please.
Hello, Jennifer. Can you hear me okay?
Yes.
Thank you for a great presentation. Definitely a lot of shared interest with my own research. I'm a faculty member at Hopkins here. So one question I have in my study is, even in your talk, you talk about like fall. Many factors may lead to fall, even vision, right? Vision loss is one of the factors. And not only, if focusing on balance, it's the same. You listed these factors that may lead to a higher issue with balance. I think from a clinical perspective, something I keep thinking about is clinicians do need to identify for a patient what's the core reason for leading to their functional deficits. So they need something that can give them the answer. In your case, whether if the person should receive cognitive training or some intervention for vestibular function. I think that's very important. So I wonder what's your insight in that?
Yeah, that's a great point. So I think, the first thing that we're trying to do is to unpack the mechanism so that we can have targeted intervention. And you're absolutely right that what will work for one person may not be the solution for others. And so something I didn't mention, but is inherent in everything that we do for all our studies, is that we do a very extensive baseline battery of tests. So we do tests of cognition, we do tests of vision, we do tests of balance, hearing, and we use the basis of those tests to look at associations with our outcome measures, but also to use them as eligibility criteria. So right now, I would say a limitation of this research actually is that we have pretty strict eligibility criteria. So all the data that I presented to you today are from younger and older adults who have normal cognition, who have normal vision, who have no clinically significant sort of balance impairments or vestibular disorders.
Mm-hmm.
And so the reason we did that is because we want to rule those out as potential confounds to our interpretations. But eventually, and this is the direction that we're going now, we want to make sure that we're more inclusive of individuals across the spectrum of different sensory and cognitive abilities so that we can map those things out more strategically and then use those to guide future sort of assessment, screening, and intervention strategies in a targeted, personalized way.
Great, thank you. Very exciting.
Great, thank you so much. I regret we don't have time for more questions. Jenny, would it be okay if people who have lingering questions get in touch with you?
Absolutely, yes. I would very much enjoy that.
Wonderful. Thank you so much. And thank you to both the speakers and to all of you for being here today. In the interest of everybody being respectful of everybody's time, it's noon Eastern time right now, and so we'll adjourn. Again, thank you very much, and appreciate everybody being here, and hope to see you again at the next quarterly meeting. More info to come by email and through other channels. Have a great day, everyone.
Thanks, everyone.